So far we have seen the fundamentals of measurements, which is common for all types of measurements. From now onwards we are going to see the specific measurements, that is what we are actually do in practice. So first and foremost and very important measurement is displacement measurement. It is important because many other measurements are based on the displacement measurement. For example, force measurement, if you want to make, force is allowed to act over a surface, and that deformation is measured by using a displacement measurement transducer. The transducer reading is converted in terms of the force units. So you will find the displacement measurement is appearing later on in other measurements also, force measurement, pressure measurements, for example, another good example, where a diaphragm is will deform when pressure acts. The deformation will be measured by a displacement transducer. We have seen as an example for a closed loop system on electronic pressure gauge. There the pressure for pressure gauge there is also a displacement transducers. So displacement measurement is one of the important measurements in mechanical measurement, and now we are going to see the first the standard for displacement or displacement or length. Length is one of the four fundamental quantities. Length along with other length, mass, time, and temperature. So when you want to, as we have seen in the earlier case, measurement means assigning a number to a parameter. Here for a displacement or length, we have to assign number for any given length in terms of standard. So what is that unit? Basic unit. That is what has been accepted by all the countries is meter. Meter is the basic unit which has been defined as length between 2 marks in some rod near Paris. That is standard. Later on we had in 1960 we had another standard in terms of Krypton 86, so many wavelengths equal to 1 meter. Now the latest standard is accepted in the year 1982 is the distance travelled by light in vacuum in a duration of 1 over 299, 792 and 458, more or less 3 into 10 to the power of 10. That is the velocity of speed, so many meters. So 1 over this number in that second, whatever the distance travelled by the light in vacuum, that is taken as 1 meter. This is latest standard which can be simulated in any laboratory. As in the case of first standard, if you want to check, you have to go to a place near Paris, but here you can allow the light to pass to travel in a vacuum chamber for this duration of second, and whatever the light that has travelled in this duration is equal to is same as 1 meter length. So that is the unit based on which the measurement is made for length or displacement. Now for the displacement measurement, the standards are available in Clark's table also. For displacement measurement, our main aim is in mechanical measurement to convert the displacement into immediately an electrical quantity. That is actually the transducer. For that purpose, we are using mostly you will find resistance, the passive elements, resistance, inductance and capacitance. These are the three basic three elements are passive elements. They are passive elements in electrical engineering. They are used. The distance whatever you want to measure is used to make some variation in resistance, or used to make variation in inductance or in capacitance, and these elements will form part of an electrical circuit, and there you will get a voltage output. This is the basis or concept of making displacement measurement by using these passive elements. First and foremost is say resistance. In this we have got two types. One resistance potentiometer, and other one is resistance strain gauge, resistance strain gauge. So these are the two ways in which the resistance made use of in measuring a displacement. And first figure shows, that is potentiometer transducer, that is our resistance potentiometer or potentiometer transducer. It's made up of a resistance Rp, it's a total resistance Rp, and whatever displacement we want to convert in terms of voltage is given to the contact point. So the contact point will be moving up and down when we give the displacement of a machine member, for example. So when that point is here, you will go EO 0, as the point moves up, you will find the total voltage of ES is distributed over the full length of the resistor. So as per the travel, you will have a voltage output. So at any instant, the displacement is Xi, and then accordingly you will have a voltage output. Now to get an equation for the output voltage EU in terms of say Xi and ES, we will derive an equation. That is, now we are connecting an instrument RM. In case if it is open circuit, A and B are open, no meter is connected, it's an ammeter, it's a voltmeter. If you don't connect this voltmeter, it's an open voltage, open circuit voltage EO. So EO dash, open circuit voltage, that will be proportionate to Xi. If Xi is 0, you have 0 voltage, and of the travel, then of the total voltage would appear here, and so on, proportionate. But once we connect a voltmeter, you find the loading effect. So loading effect, what we have learnt earlier, that will come into picture. So then it is no more, the output voltage is no more linear with the displacement. For that we will derive an equation. So before connecting the voltmeter, whatever be the resistance output as seen from the points A and B in the circuit, A and B, then we will say the RO, the output circuit or output resistance of the potentiometer circuit is that is, we have to go from A to B. From A to B we have to go, that is why we have to find out the equivalent circuits. From A to B, one resistance Ri corresponding to Xi, and the other resistance is parallel path is Rp minus Ri, and again you can come to point B, and ES is short circuited for the purpose of equivalent resistance. So now RO is made up of two parallel resistance. So and then it is equal to RA RB, that is Ri into Rp minus Ri. These are the two parallel resistances divided by the summation of these two things. So Ri plus Rp minus Ri, that you will have Rp. So this is the output resistance. Input resistance is Rm. So EO by EO dash is the open circuit voltage of the circuit at AB. So EO by A dash equal to 1 over 1 plus RO by Ri. So RO is equal to this one, Ri into Rp minus Ri divided by Rp, and the whole thing is divided by Rm. That is, Rm is our input resistance. So this is our loading effect. Now this expression can be transformed in terms of Xi and Xt, and also ES in place of EO dash by using the equation EO by or EO dash by ES. EO dash by ES is equal to Xi by Xt. This is one relation. That is, open circuit voltage is always proportional to Xi. That is one equation, and then Xi by Xt is equal to Xi by Xt is equal to Ri by Rt. So using these two equations, the equation for loading effect can be rewritten in terms of EO by ES. EO by ES is equal to Xi by Xt divided by 1 plus Rp by Rm into Xi by Xt into 1 minus Xi by Xt. So this is the equation in terms of ES and Xi by Xt. Now suppose Rm is infinity, suppose Rm, that is meter resistance infinity, you will find when Rm is infinity, Rm tending to infinity, then EO by ES is equal to Xi by Xt. That is, EO is proportional to Xi, because then you bring this side, ES this side. So, ES is constant, Xt is constant, total travel. So, EO is proportional to Xi. That is what you have got in this characteristic equation. The plot, the same equation, EO by ES, that equation is plotted here. We find the curve 1 Rp by Rm is equal to 0, that is Rm is infinity, then you will find is linear. That is, EO is proportional to Xi by, this is Xi by Xt, proportional to Xi, Xt is constant, Es is constant. When the Rm is having definite value, then we find there is no more linear, the EO is not linear to Xi, then you will have non-linearity comes into picture. So, 1, 2, that curve 2 is for 0.1, Rp by Rm is equal to 0.1, and curve 3 is for 0.5, the ratio, and for 4. See, when the ratio increases, you will find non-linearity also gets increased. So, in order to keep the error within limit, loading effect within limit, Rp by Rm normally selected as 10, 1 over 10. So, that meter resistance should be at least 10 times the resistance of the total resistance of the potentiometer in order to have the error within limit. Now, the potentiometer is also used for the rotary motions. So, this is for rotary motion, that is, the total resistance is arranged in a circular fashion, and you have the supply voltage and the contact here. Also, we have the potentiometer, it is called multi-turn potentiometer. So, say it may be 10-turn potentiometer, that is, here its construction is, we have here screw thread, this is a screw thread, you have a screw thread. So, as you rotate, the nut moves to and fro, and the travel is restricted between these two limits, and for making the full travel, probably you have to make 10 turns. If you make 10 turns, then you will find the total travel is there. So, proportional to the number of turns, you get the output voltage here. These are the various constructions of the potentiometer. But you find in selecting Rp value, you have to be little bit careful, because it has got certain opposite effects. See, Rp should be, here you find Rp should be small compared to Rm in order to have loading effect smaller. So, Rp should be small to have smaller loading effect. But when we consider the sensitivity, here sensitivity is equal to dEO by dXi. Xi is the input motion, EO is the output. So, dEO by dXi is equal to ES by Xt. This is our sensitivity of this potentiometer, resistance potentiometer. Now, sensitivity is proportional to ES, that is supply voltage. Higher the supply voltage, higher will be the sensitivity for this transducer. But you will find, to have the higher ES, then we find the power rating. Power rating is equal to P is equal to ES squared by Rp. This is the power rating of the resistor, or the manufacturer will specify that much power alone it can dissipate. So, when you want to have larger ES for larger sensitivity, the power is always constant. When you increase ES, you have to correspondingly increase Rp also. That means, to have higher sensitivity, you should have higher Rp. So, Rp should be high for higher sensitivity. So, now you find contradicting requirements for Rp. Rp should be small for smaller loading effect, but it should be large for higher sensitivity. So, hence selecting Rp we should be careful. So, if you increase too much, then you will find you have got loading effect. These are the considerations when selecting Rp. And now we have the potentiometer, sometimes single wire potentiometer. So this is a single wire potentiometer. This may be moving to and fro. Here you have the voltage supply. This is a single wire potentiometer. The advantage of the single wire potentiometer is resolution is high. Resolution is high. That means you can have more movement of the Xi as small as possible. You will have the output, corresponding output. But the problem here is the voltage ES cannot be large because this resistance is small. So ES cannot be small, cannot be a large value for having a larger sensitivity. So to increase the value of ES, you have to have the larger length for the wire, resistance wire. That is achieved by having a wire wound potentiometer. This wire wound potentiometer has for a given length length of potentiometer, you have larger wire wound over a spool. But the problem here is the wire wound potentiometer, the problem is the resolution is low. The resolution is low because we have the wire windings, one windings here, another winding there. So this is a spool. Similarly, this side also. So when the contact is here, you have one voltage, and until it jumps until it moves over to another wire, the voltage output will be same. So the resolution here is equal to pitch of the winding. So pitch of the pitch of the winding is equal to resolution. Now if you consider the single conductor, within the conductor the voltage doesn't change, voltage output. That means from the middle point, putting the error plus or minus of the distance here, of the distance other side, you don't get any output change. That is error. Even though motion is there over the conductor, there is no corresponding change. That means error is equal to plus or minus of the resolution. So of the resolution, because resolution is more or less equal to the pitch distance, or equal to pitch distance is equal to the diameter of the wire. So that's why we say our error is equal to half of the error is equal to plus or minus of resolution. So these are some of the characteristics of a potentiometer. A resistance potentiometer, what you have seen, is a very old device, primitive, but still it is used nowadays. Also it is used. Next form of usage of resistance is resistance strain gauge. Very widely used in mechanical engineering as well as in civil engineering to find out the stress in beams at different points. Very widely used. This effect was found out by Lord Kelvin in the year 1856. Yeah, 1856. Lord Kelvin found out this effect. when your metallic wire is strained, the resistance is changed. That is physical effect that is being made use of there. Now there are in the strain gauge there are two main types. One is unbonded strain gauge, other one is the bonded strain gauge. Unbonded strain gauge came earlier, that is first it was made in 1931. Yeah, 1931. This came into picture 1937. So such an unbonded strain gauge, one such strain gauge usage is illustrated in this figure. How this unbonded strain gauge is fabricated and made use of. And the bonded strain gauge which came later, you find again there are two types, wire gauge and foil gauge. In wire gauge itself you have got flat grit and helical grit. Flat, that is made up of wire. Here it is foil. So the wire is found in two different ways, flat grit, that is what is shown here, flat grit. So wire is taken in zigzag fashion, and whole thing is fixed in paper or plastic backing, two such packings, and there will be cement to hold this in between the paper packing, and you will find the whole thickness, this wire is of the order of 25 microns diameter, 25 microns diameter, and with the thickness of the paper and the cement and everything will work out to 70 micron. Whole thickness of the strain gauge will be 75 micron, so to say. So, this is a flat grid. Instead of flat grid, it's also we have got helical grid available in the market. That is, you have a core, a paper core, whatever it is, a flat piece. On this, in helical fashion, the wire is wound. Same wire is wound in this, and the whole thing is embedded. Whole thing is fixed in two paper packings or plastic made up of plastic backing of very thin, very thin. And the total thickness of the whole strain gauge will be of the same order, 75 microns. They are also available, because here it is helical grid, is easy to wind and make it. Whereas the foil gauge is made up of electrochemical machining, electrochemical etching, electrochemical etching process. By that we make this foil gauge. Here the thickness is of the order of 4 microns. The whole thing is again fixed in paper, thin paper, and with the cement it is held there. The main advantage of this foil gauge is for a given cross section you got more surface area, and also it is a rectangular cross section, the whole configuration. So it gets better bonded than the wire gauge to the any base material. And since surface area is more, we find it is heat conducting capacity also is more in case of foil gauge. So nowadays you have foil gauge are easily available in the market. So these are the different types in bonded strain gauge. Mainly 3 types in bonded strain gauge, and unbonded strain gauge the usage is illustrated here. We have, for example, we have a fixed base, and it is surrounded by a moving frame supported by springs, say 4 springs, leaf springs. Yeah, it cannot stand just on in space. So from the base, it is the moving frame is supported from bottom. Say 2 or 4 numbers, we can support this frame. It's a moving frame. This is the moving frame. Moving frame means it is within the gap only it can move. Later on it will be hit this middle projections, fixed base. So within this gap it can move. With the spring support will deform. When you move this, the spring support will move. And this motion of the frame is measured by using the 4 wires, that is wire 1, 2, 3 and 4 wires. Now the wires are fixed in such a way that it is elongated, it is pulled little bit and then fixed to the pin here. That is in the assembly condition, you have to assemble the wire under strain. We find the 2 strains or 2 wires are pulling the frame. See in this direction, the other 2 wires will pull in the opposite direction. So 2 wires pulling in one direction, other 2 wires pulling in the opposite direction. Net force on the frame will be 0, and so it will take a neutral position when you assemble all the 4 wires. The wires are assembled in tension. It is because the wires cannot take any compressive load. It will buckle. So in order to use this instrumentation for both the direction of motion of the frame, when we want to measure, then the wire should be assembled under tension. That is, the natural distance between the frame point in the frame and this will be smaller. So you have to pull it and then assemble the wires. And now you find, suppose we give you a motion. So in this direction, left to right, we give you a motion to the frame left to right. Of course, motion is limited, say 1 mm, within 1 mm only. So if assuming the gap is 1 mm, within 1 mm only we can give the motion. Suppose it moves this direction, what will happen? The tension in wire 1 and 3 will increase, and the tension in wire 2 and 4 will decrease for this motion. So that means 1 and 3 which are connected in a bridge like this, where the tension is increased are opposite arms, and where tension is decreased in the other pair. So you will find 4 times it is a full bridge. Say in 2 wires tension is increased, other 2 wires tension is decreased. So you find a resistance increase in the opposite pair, in the other opposite pair resistance is decrease. So you find a full bridge effect there. That's how the 4 wires. That's why it's called unbonded strain gauge. Strain gauge is made up of the 4 wires. Now we have all the semiconductor strain gauge also available. They have got very high gauge factor. Now, what is a gauge factor? We will derive an equation. Gauge factor of strain gauges, gauge factor. See, for any metallic wire, R is equal to resistance of the wire is equal to rho L by A, where rho is the resistivity and L is the length of the wire. So suppose this is the wire, this is the wire, length of the wire, this is the area. A is the cross sectional area. So R of this conductor is given by this equation. Now take logarithm on both sides. Log R is equal to log rho plus log L minus log A, and differentiate both sides. Dr by R is equal to d rho by rho plus dl by L minus dA by A. That is differentiating this equation. Different equation 1, we get equation 2. Now dA by A, now A is equal to pi d squared over 4, pi d squared over 4, that is d is the diameter of the wire. So if you find dA by A, you will get from this you will get dA by A is equal to twice d by d, by d 2 twice dd by d, and that is equal to, in terms of Poisson's ratio, minus 2 nu dl by L, because the contraction is proportional to the Poisson's ratio in terms of linear strain. So we get nu being Poisson's ratio. Now substituting this equation, this in the equation 2, you have got dr by R is equal to d rho by rho plus dl by L plus 2 nu dl by L. Now divide the whole equation by dl by L. So dr by R divided by dl by L is equal to 1 plus d rho by rho divided by dl by L plus 2 nu. Now this dr by R by dl by L is called the gauge factor. This is the gauge factor of the strain gauge. What does it represent? The relative resistance change to the strain per unit strain. That is the definition for gauge factor. Relative resistance change per unit strain, that is the gauge factor, which is equal to 1 plus 2 nu. Nu is the Poisson's ratio. For steel it is around 0.3. So twice 0.3, 1.6. 1.6 comes from the due to strain, due to strain, and the other portion d rho by dl by L is called piezo-resistive effect. It is called piezo-resistance effect. Piezo-resistance effect. For a metallic wire, generally the gauge factor is around 2. So you find here 1.6, 0.4 comes from this piezo-resistance effect for metallic wires. Whereas for the semiconductors, we have got the gauge factor for semiconductor strain gauge is around say 100, 120, whatever it is, very large number, and that is mainly due to the piezo-resistance effect, d rho by dl by L. That is, the resistivity of the material itself is changed when there is a strain, in the semiconductor material. Now we will see how the strain gauge is made use of in measuring displacement. In potentiometer, what you have given is the displacement is given to the point which moves over the resistance. Here how it is done. Say for example, if you want to measure displacement, give it at the end of a cantilever. This is a cantilever beam fixed at the fixed here, and the free end you give this motion. When you give the motion, you find that near the fixed end of the cantilever you have got stress and strain. So the strain is picked up by the strain gauge. For this purpose, what should be done? You have to fix the strain gauge at the suppose this is the plan of this is like this. You have to fix the strain gauge here. For this purpose, you have got so-called cement the manufacturer who makes this strain gauge also supplies cement. So with the help of a cement, suppose with the help of a cement, you have to fix the strain gauge to the base metal, and then you have to wait for put a small weight over it and wait for a few hours, 6 hours or 12 hours. Then you will find the strain gauge will become part of the metal. That means whatever the strain that happens that occurs in the base metal or the cantilever, it will be transferred to the strain gauge. It is because, as you have seen in the flat grid, see, flat grid is somewhat like this, embedded between the plastic or paper packing, and if you have the cut section, suppose you cut it here and see, you find the paper is there, and then another paper, and in between you have got this cross section of the wire, and this is filled up, the space between the wire is filled up with cement. Here also we have got cement, yeah, this also cement, completely filled. There is no gap between the wires, there will not be any empty gap, all the space is filled up with the cement. Because of this construction, we find the wire can also take up any compressive strain. Free wire cannot take compressive stress or strain because it will buckle, but here there is no space for buckling as it is manufactured. So the wire can take up both tensile as well as compressive strain. So such a strain gauge is pasted, one for example one at the top of the cantilever, and the displacement is given here. There is displacement. Suppose due to this displacement, this will bend like this, this will bend like this. To that extent it is strained. That strain is picked up by the wire, and when there is a strain, what is strain? Strain is equal to dl by L. That is our strain. What you have seen in the equation, dl by L is the strain. When there is strain, then corresponding you have got the gauge factor multiplied with the strain, you have got this resistance change in the strain gauge. This is what is happening. So you give the motion to the end of the cantilever, and the motion is measured by using the strain gauge. So in this process, we should know the direction of the strain. Here we know in the cantilever beam, the top layer will be tension, and bottom layer will be top layer for this is here. That is, for this type of motion, here will be tension, there will be compression. We know that happens along the length of the cantilever. So we know the direction of the stress and strain. In such cases, it's sufficient if we make if you can paste this. This is the axial length of the strain gauge. That is along the axis of the cantilever. You can fix it. That is, it will be same in the same direction of the strain. It is fixed. Suppose in some fixtures, some structures, you will find the direction of the strain will not be known. For example, in rocket panel structures, you will find due to acoustic stress or strain, the panel is strained in all directions. So we find no fixed direction can be fixed. In such instances, what is done is we go for the strain gauge rosettes. This is strain gauge rosettes. We have got two types of rosettes, delta strain gauge rosettes and the rectangular strain gauge rosettes. That is, three strain gauges are fixed. Say in case of rectangular rosettes, it's 90 degree and the middle is 45 degree. It is fixed there on this structure. Similarly, you can go for delta. So these three strain gauges, epsilon 1, epsilon 2, epsilon 3, is fixed on 60 degree to each other, and measure each strain separate circuit you will have. Measuring each strain, then you can find out the principal strain. You have got formula that can be referred in standard textbooks. By measuring the three strains, the principal strain, axis of principal strain as well as principal strain can be computed in terms of epsilon 1, epsilon 2, epsilon 3. That is, in case you do not know the strain or stress direction, you have to go for the three strain gauges fixed on the structures, and from there we can find out the maximum strain produced in the structure where we have fixed the strain gauge. Now this strain gauge has got so called, when the strain gauge is made up of like this, when you find when the suppose the strain is in this direction, unidirection, one direction, we have got two segments. One is along the axis, say segment 1, and there another segment 2 transverse, that is 90 degree to this axial direction. See, it is a loop, it's made up of loop. you have got here 1, 2, 3, 4, 5 loops are there. So for a given strain in one direction, axial direction, the segments similar segments say 1, 2, 3, 4, 5, 6 segments and axial directions, and you will find 4 segments, 1, 2, 3, 4, 5 segments in the transverse directions. So what happens for this tensile, for example, it's tensile strain, the linear along the axis the wire will extend, the tension will due to tension it will increase, so resistance will increase. But for that for the same strain you will find the transverse directions, the cross sections increase and you will find resistance is decreased, rho L by A. So when A is increased, R is reduced. So for a given for axial strain you will find some portion of the strain gauge it is reduced resistance, some portion it is major portion is increased resistance, and a smaller portion is decreased. So you will find net effect on the strain gauge for an axial strain is reduced. This is called transverse sensitivity. Transverse sensitivity. But in most of the strain gauges, the perpendicular segment portion of the total wire is very small, hence the transverse sensitivity will be low. So this is one of the error source. So that is normally small since the segment perpendicular segment is small. Second error source is temperature. Temperature is main error source in strain gauge measurement. Suppose we are using one strain gauge, quarter bridge. It is used in quarter bridge. So quarter bridge like this. That is only one is active arm. That is R1 is active, R2, R3, R4 are constant resistances, and we get output voltage here EO. Then you find there are due to temperature there are 3 effects noted in the strain gauge. First one is the strain gauge wire itself expands when the temperature is increased. That we know the equation RT is equal to RO into 1 plus alpha T minus T0. That is a coefficient of resistance alpha, temperature coefficient of resistance. When R0 is a resistance at T or degree centigrade, then RT at any other temperature T is given by this equation. When T is increased, you will find RT is increased. There is one effect. Secondly, you find that differential expansion. The wire material, you will find there are 2 types of wire material. One is advanced alloy. Advanced alloy. It is nickel and copper, made up of nickel and copper, and other one is isoelastic. These are the 2 types of material used for strain gauge. But suppose we fix this strain gauge over a mild steel or some other material, you will find the linear coefficient of linear expansions are different for the strain gauge wire and the base material. Then you will find there is a difference in expansion of the wire gauge material and the base material. Due to the difference of this expansion, suppose you find the base material where it is fixed expands more than the strain gauge wire, then for any given temperature rise, the wire will be pulled by the base material. That is, all these things are happening without any input signal. Without any input signal, just because there is temperature increase, you find resistance is changed when due to temperature rise as per this equation. Again, it is being pulled by due to difference in coefficient of thermal expansion, it is being pulled. Again strain, that is another source. Third, you will find creep. When the operating temperature is more than 200 degrees centigrade, so called creep occurs. Creep is a phenomena when the load is constant, there is the deformation continues, more and more deformation comes. That is creep. That also will be there when the operating temperature is more than 200 degrees. Otherwise, you will find due to temperature alone we have 2 different effects, and this gives output voltage even when there is no change in no input signal, there is no displacement we have given. So this is compensated what we have learnt already under bridge circuit by using a dummy gauge. This we have seen under bridge network. That is, we put another strain gauge fixed to the same base and don't load it and keep it in the same atmospheric conditions, and you will find whatever the temperature increase is there, that will produce similar effects on both of them, and similar effect put in adjacent arms. The R2 will be now dummy gauge. similar effect in adjacent arms get nullified. So when the temperature is there, that effect will be nullified, no EO will be appearing due to this temperature effect. And this is one way. By using a dummy gauge we can compensate, that is for a quarter bridge. For off bridge we know that is off bridge. There are two situations you will be using off bridge. That is when the stress and strain are opposite in polarity, you are connecting in the adjacent arms. That is one is in tension or resistance increase, other one is resistance decrease. Then you will be using in adjacent arms, that is opposite effect we are putting in adjacent arms. Adjacent arm. When we have the similar effect, that is similar effect that we have learnt under the bridge network, similar effect in opposite arms of the bridge. But when it is opposite effect, that is a cantilever, for example, opposite effect is there in a cantilever, we have learned. So this is what is displacement is given. One is top, one is bottom. So here tensile strain, and here you have got compressive strain, that is opposite in polarity, and these two strain gauges are connected as adjacent arms. In this case, the temperature is similar effect gets cancelled automatically. Whereas if you are using the similar effect, that is putting the strain gauge, two strain gauges at the top of the cantilever itself, then both the strain gauge will be picking up a similar strain, tensile strain. Then we are putting the opposite arms. If you put opposite arms, temperature effect also gets added up. In that case, you should go for two dummy gauges. The two dummy gauge in plus one dummy gauge, you put one more dummy gauge, same material dummy gauge, and here you got two, one behind the other, and here you will have the because all the four strain gauges will be simultaneously affected by this temperature, and you will find that effect will be 0. So in case of the similar strain, we have to use the other two arms as the dummy arms and connect them accordingly in the bridge network. If it is a full bridge, so that is in the cantilever. So suppose this is the cantilever. This is X side displacement. So displacement is given there, and we have the suppose this broad sheet made up of, and you have got two strain gauges R1 and R3, and that is R1 and R3, one behind the other, and we place other two pair R2 and R4 at the bottom of the cantilever. So that means all the four are active, and two in one direction, other two in opposite directions. In such a case, you find the temperature compensation is automatically there. So since all the four arms will be affected in similar way by temperature, it gets cancelled out. Whereas signal is opposite, you will get proportional to the signal. So that is the temperature compensation for different usage of the strain gauges, either quarter bridge or off bridge or full bridge. You have to adopt this temperature compensation. Now one more point you have to see is signal noise ratio. In most of the applications, we find the strain produced in the base member should be of sufficient magnitude. If it is very small, you find signal noise ratio will be very small. If the strain produced is small, then voltage output will be small, and the noise in the instrument may be more. Noise is coming, we have learnt under amplifier, Johnson's noise, and so in terms of some microvolt will be there, and our signal should be much more than that noise. This is what is meant by signal noise ratio. Otherwise, if signal is small, say if signal is also of the order of few microvolt, that will be lost in the noise. So you don't get any which is signal, which is noise, that can be found out. So signal noise ratio is of around 100 or 200. We should ensure. That is possible only if you deliberately make a bar. Suppose you want to fix a strain gauge over a bar. Suppose this is a bar. If it is an existing bar which has been designed for the strength. If it has been designed for strength, and pasting strain gauge on this, you will have the only very small strain only will be there, small strain. and in that case voltage produced from the bridge will be very, very small, signal noise will be small. So what you are supposed to do is weaken these cross sections, so make it smaller dimension and then put your strain gauge here. So this is little bit problem in the sense you will find that dimension will be small for a larger strain and you cannot paste it. For that purpose what is done is instead of a solid piece you go for a tubular constructions. So from here to here you have the tubular constructions and you fix with a flange you can fix. Have a flange with a bolt and middle portion alone is the tubular, the other portion are outside it is solid piece. Now you can paste your strain gauge, one here, one at the other side, and so 2 or 4 means Poisson's configuration you have to fix. So you have to ensure sufficient signal noise ratio. That is possible only if you weaken the surface, sufficient noise ratio will be there. As an example, it is worked out. Suppose there is a strain of or a stress of 60 bar, 60 into 10 to the power of 5 Newton per meter square, so many pascals, Newton per meter square. That means stress is there in a rod, and we are using one strain gauge of 120 ohm, 120 ohm strain gauge. Gauge factor is 2.1, and in this case EO will be output of the bridge, quarter bridge will be 0.11 millivolt. So EO from the bridge will be 0.1 millivolt for a stress of this, and Young's modulus is 2 to E is equal to Young's modulus 2 into 10 to the power of 11 Newton per meter square. So we have for this we have a strain of 3 into 10 to the power of 5, 3 into 10 to the power of minus 5. This is a 0.3 micron, and that is giving rise to EO, which is equal to actually it is obtained 14 ES into Eg epsilon. That is the output of the bridge, and this supply voltage is assuming for a strain gauge 30 milliamp, because this capacity of the strain gauge to dissipate the heat energy limits the current carrying capacity. For 30 milliamp and 120 ohm as the resistance, you have got 2 ohms will be there, 2 ohms across this voltage supply. So 240 ohm into 0.3 milliamp running will give rise to a voltage of 7.2 volts. So 7.2 volts supply ES, and G is 2.1, epsilon we have found out. So we find a voltage output of 0.11 millivolt. And for this if you use an amplifier, the noise voltage Vn is obtained as root of 4k TBR, where T is the temperature, higher temperature, and K is the Boltzmann constant. This is Boltzmann constant. B is the bandwidth. B is the bandwidth of the amplifier, and R is the resistance of the strain gauge. Now if you substitute, here you will have around 0.45 microvolt. So noise voltage, this is the noise voltage. Noise voltage is 0.45 microvolt. Our signal is 0.11 millivolt, giving a signal to noise ratio, that is noise is equal to 244:1. 244:1. This is a good signal noise ratio. Suppose the stress is instead of, that is the case when we are weakened. When we are weakened, you will have sufficient stress. Suppose we paste the strain gauge in the existing rod, and if it is the stress is only this much, 0. Stress is equal to 0.060 into 10 to the power of 5 Newton per meter squared, then you will have EO as EO is equal to 0.11 microvolt. 0.11 microvolt. That is, in this case we will find noise is larger. Noise is 0.45, 4 times larger. So we find signal is lost in this case. That's why we should not paste the strain gauges on any existing rod. any existing machine. Suppose we want to find out stress or strain in a automobile part which has been designed already for strength, there we should not paste the strain gauge. That part you have to remove it, put a weaker part and paste it, then you will have sufficient stress strain. That is, you are deliberately weakened the part, but the weakening should be done below the yield stress. If you go to plastic region, then it is plastically deformed, it will spoil the whole thing. So within the elastic limit, you have to weaken the part and then paste strain gauge, so that we can have sufficient signal to noise ratio of the order of 244:1.